Good evening, everyone. Have you been enjoying the presentation so far? Very informed, very encouraged, and faith-affirming as well. Our next presentation will be by the chair of the Physics and Engineering Department here at Southern, our very own Dr. Ken Caviness, will be sharing with us about the limitations of science and how to relate science and faith.
Thank you very much. And we have some slides that should be coming up for this presentation. And while the computer is waking up, let me again thank the presenters from this whole weekend. I've really been enjoying these presentations, and it's an honor to be a part of this as well. The first slide that we'll see in a moment gives the title and also a link that you can get some more information because the material is mostly taken from a paper that I wrote a few years ago, which is in the Journal of the Biblical Foundations of Faith and Learning, which is a conference that Ed and Ann Zinke supported and was put on at Southern Adventist University, and it was my privilege to be part of that as well. And I know I sent the PowerPoint, so I'm sure that pretty soon we'll have that showing up. There we go. So I am Ken Caviness, and until this past week, I introduced myself as chair and professor of the Department of Physics and Engineering, but we are now the School of Engineering and Physics. Great excitement, a lot of things happening here in our area. The presentation that I'm going to share with you now, history highlights the strengths and limitations of science. Originally, as I mentioned, this was from a paper that I wrote, and I was focusing on the limitations of science because as a scientist and as a Christian, I need to understand when people say, oh, science has disproven such and such. And I'd have to relate to this. I have to think it through. But I began thinking that it's more than just looking at the limitations of science. I need to present a balanced picture. Science is incredibly useful and has strengths. So we'll look at both. Science is hugely successful. I look around, I see all the accoutrements of a technological civilization, and I see science works. We're surrounded by this. So a few pictures there, different areas, different fields, and you can see that science works. So I might call that a proof by example, and I put proof in parentheses because it's not proven, but it's very strong evidence. Science works, and we use it. I use it every day. I teach science, and I present to my classes the power tools. What are the strengths of science? So real quick here. We reduce problems to things that are simpler, and in fact, we break the problems into smaller pieces that we can handle. So more easily treated. That's a useful skill. And another that's almost as important is just take a simpler problem. Real life gets complicated, gets messy. So we take an approximation, and then we'll look at adding back in some of those complications as we proceed. And we model things mathematically. Galileo said, mathematics is the language God used to create the universe. And it's the language we use to describe God's creation. So it's very important for me to be able to do some math, model what I see. Another very important principle, and I'd call it a power tool of science, is Occam's razor, sometimes called the principle of parsimony. I take the simplest example that works. So I'm not looking for complicated explanations. I'm looking for simple explanations if possible. But I do need one that works. I'm not going to take something so simple that it doesn't work. So quick example of reduction. So reducing a complicated problem to several parts. You see here a bouncing ball. But the pattern, the trajectory of the ball is complicated. It's moving up and down, it's moving somewhat to the right. Now, we have experience with throwing and catching balls, but this is a complicated problem. I can reduce it to two simpler problems. I can divide out the vertical motion and the horizontal motion. It turns out to be much, much simpler, both of those. And actually, this example is from why I became a physicist. I was a senior at Fletcher Academy, and I had this explanation given to me that you can take this complicated trajectory and explain it by two separate simple problems. And that excited me, the power to be able to explain things. So I went walking up and down the hall of the dorm, throwing my keys in the air and catching them. And guys came around, what's wrong with Ken? You know, so, but this was the beginning of my decision to study physics and actually to try to explain to other people. So it means a lot to me. And you don't have to know these math equations, but I assure you, they're pretty simple compared to the complicated problem that we started with. So we use the scientific method. We do expect to use real world observations and explain them. Look at patterns. I love patterns. And then try to find possible explanations. And here's a key point. Mostly we eliminate things that don't work. People can come up with explanations and we can sit around and discuss it, but until we test them, there's really not, I would say we haven't done science yet. So those are the things, and I would say these are real strengths that help us use science. It's really, I would say it is the most powerful tool God has given us, the rational thought. But it has limits. Let's look at that. So some people think that science is the only way to prove anything, and I'll even say the only way to truth. No, that is not a scientific statement. That is a statement of faith when you say that. And in fact, it is scientism. It's not science. So I don't have that kind of faith myself that science is the only way to know truth. In fact, I would say it's false. And I'd like to take you through a little story, some from history. I love history also. And some of these examples Dr. Clausen has touched on earlier today. So this fits in very well with our weekend. And I'd like to convince you science is not in conflict with the Bible. So we will finish up by looking at what does a biblical worldview, how would science based on a biblical worldview look? So real quick, there are certain human reactions that could occur if I come up with a conflict between experiment and theory. So I have my wonderful theory, and then I do an experiment or an observation, and it doesn't agree. So here are the possible human reactions. We could deny. We've heard of deniers in various topics. We could just ignore the problem and go on. I cling to my trusted theory, and that could be any sort of theory, and I just refuse. It's almost like the ostrich putting its head in the sand. I won't look. Another possibility, I could say, yeah, this is a problem. I'll modify my theory. I may have to give up some pieces of it. I may have to modify it, and I'll go on. To me, that's perhaps a more mature reaction, but all these are human. Another possibility is we may have to just replace it altogether. Sorry, this theory, I thought it would work, but I know more now. I've got more data, and it fails. Let's try another theory. So in all these options, science really can't tell me what is the truth, but we can look at this in history. We can see how these reactions have played out. In all cases, we'll see science is tentative. So from history, we'll go back to the geocentric model, and Aristotle said, this was an idea of the time, the Earth is the center. Geo, Gaia, the Earth, center, so everything's centered on the Earth. Don't laugh, it made sense. If I drop a rock, it falls down to the Earth. And part of this model was earthly matter falls back to the earth. It wants to return to its natural place. Drop a ball, it falls to the earth. Every time I dropped something, it fell to the earth. So Aristotle's explanation is it's earthly matter. It's doing its thing. And heavenly matter, celestial matter, so the ethereal matter, as Dr. Clausen used the expression last night, stays in the heavens. And in fact, it's going to circle because, according to the Greeks, the circle is the most perfect geometric figure. So things on earth act different from things in the heavens. On earth, it falls straight down. So clearly the earth is the center. And also we have some other features. The sun rises and sets. The moon rises and sets. I see stars. Things seem to circle the earth. Things in the heavens. Things on earth fall to the earth. So this is the model. And it, to a certain extent, explained things. That's what science is supposed to do. It's supposed to explain things. But there were some problems here. And what was the human reaction to the wanderers? The Greeks actually used the word. In Greek, it's planetai. So the wandering stars. They didn't fit with the pattern. Every night I look at the constellations, they seem to have a fixed pattern, except these bright stars, the wanderers, sometimes move faster than the background constellations. And sometimes they actually back up. That's called retrograde motion. These couldn't be explained. So the figure at the bottom left here shows the path of Mars. You see the red dot, red planet, passing through a constellation and then backing up and then going forward again. Well, that's complicated. You can't explain that with heavenly matter just circling the earth as the center of the universe. This doesn't work. So what's the reaction? In this case, modify the theory. So they didn't want to give up the theory, but they saw they have to modify it. We're going to build in something extra. And this was done by Claudius Ptolemy. So roughly 100 years after Christ, the idea that, yes, everything circles the earth, we still believe that, but it's on an epicycle. So a little Greek lesson, epi means on top of. So a cycle on a cycle is what we're saying here. You can get this exact same effect if you put a dot on your bicycle wheel and you watch it go. So your bicycle is going straight, but the wheel, the dot, is doing this number. It's an epicycle. So he says, Ptolemy says, Mars is orbiting the Earth, but it's on an epicycle. And so sometimes it goes, oh, we can model this. Watch the image. It sometimes goes forward and sometimes goes backward. Wow, that, from our perspective, that's exactly what it does. This is great. We fixed our theory, right? So this model, the epicycle geocentric model, modification, was used for over 1,000 years, about 1,400 years. Wow, it gave good predictions. That's an extremely successful theory. And it's also just wrong. So a theory can exist for 1,000 years, be used, be useful, and still be wrong. So this is a cautionary note. It was eventually replaced by a better theory, and that teaches me even long-lived theories, we should treat them as tentative. So the better theory, in this case, we'll see the better theory was not to modify, but to actually throw away. When we come to Copernicus, let's just move on. The next case, replace the theory by a new model. So Copernicus, he looked at things in a different way. And he said, it really looks like the sun is the center, the earth and other planets are orbiting it. That's the model that I grew up with, and you did too. But in 1543, this was a new thought. Copernicus was smart enough to wait until he was dying before he published the book. So he avoided the problems of being pulled up in front of the Inquisition and so on that way. So on the revolutions of heavenly spheres, he's still explaining the heavens. He's seeing orbits, revolutions, he's seeing circles, but he doesn't need epicycles. And here's why. The sun is now the center. The Earth is orbiting the sun. Other planets are also orbiting the sun. Heliocentric, centered on the sun. So this animation shows two dots orbiting the sun. We have the blue dot, that'll be the Earth, and Mars will still be the red dot. From our point of view, sometimes Mars crosses the sky and sometimes it seems to back up. But that's because we're moving, right? You've had this experience as you sat at a stoplight ready to step on the gas, and suddenly you wonder if your car is rolling. And it's not. It's the car next to you that was moving, and motion is relative. And you felt like, oh, maybe I'm moving. No, it's him. Okay, so from a moving platform, we have this more complicated thing going on. I do see Mars cross in front of me and seeing pass in front of other constellations, other stars, but it's explained, the complication of the motion is explained because I'm on a moving planet. It worked. It was lovely. And in fact, this was conceptually simpler. Now, little proviso, if we looked very carefully at the predictions, it's no better. In fact, it was in some ways a little worse. So if you're just looking at predictions, you might have a hard time deciding which theory. But we have simpler paths, and of course, we don't have epicycles for the sun because the Earth is simply orbiting the sun. We don't have epicycles for the moon because the moon is actually orbiting the Earth. But this more elegant model, simpler, more powerful, it was great. And in fact, it did eventually predict stuff better. That's what I'd like science to do. It should give me a deeper understanding of what's going on. So we come to Galileo, and we've heard some already, but let me just say, Galileo, amazing scientist. He wrote a book in which he talked about two kinds of science. He meant theory and experiment. And we consider Galileo basically the father of combining, using both theory and experiment to assist each other. Theory teaches you what experiments to try, and experiment teaches you what theories you might try. Very powerful. Might call him the founder of science. And many areas we still base our basic ideas on Galileo, his understanding. But he also turned a telescope to the heavens and he saw, oh wait, the sun is not perfect. It has sunspots. The moon is not perfect celestial matter. It has craters. Venus has phases. And that's explained because sometimes it's closer to us, sometimes it's on the other side of the sun from us, as both Venus and Earth orbit the sun. Explained very well. And Jupiter has moons. We still call them the Galilean moons, the first four. Sometimes come Friday evening, once a month out here in the Hickman Science Center parking lot, we have the telescopes out. And you can see the moons of Jupiter, little bright stars in a row. And those are orbiting something else, orbiting Jupiter, not orbiting us, not orbiting the sun. So the sun is not the center of everything. The Earth is not the center of everything. Things orbit other things. So Galileo brings more data to our explanation. And eventually that data disagreed with Copernicus also. So what do? Do we deny the new data? Do we modify the theory? Do we replace it? In this case comes Johannes Kepler, and he modifies the theory. His modification is heavenly things don't go in circles. They go in ellipses. The shape is different. He also predicted the speed of the planets moving around the sun. He predicted the total period of a planet orbiting. So those are Kepler's three laws, and they explain the shape, the speed, and the period of the orbits. Works very well. Works better than anything we had before. Science marches on. We do better. Well, in just a few, in this case, 3 general statements, he is able to explain so many things. But has he gotten to the truth yet? Well, it may be more true, but I still have no proof, right? I could wait 1,000 years and still find that he was wrong. In fact, in this case, I'd just say it's a better model. We don't have the earth at the center. We don't have circle is perfection. We do explain many, many things, and that's good. That's what it's about. But that's not the end of the story. Isaac Newton explains all Kepler explained with just one law. Now, Newton was an amazing guy, and we won't take more time, but he had to invent calculus in order to do his physics. Amazing. But that equation at the bottom, no quiz, the force of gravity is a very simple formula. And every 2 masses in the universe attract each other. That's what Newton says. And it depends on the distance between them, the r squared in the denominator. So simple rule explains basically everything. So that's a win. That is amazing. And here was a test. It was an accidental discovery of a new planet. Sir William Herschel aimed his scope at the sky, and he saw a brand new planet, the planet Uranus. And this gives us a chance to test our theories. First new evidence. Well, it worked, but it's not proof. It's confirmation. It's confirmation, and I like it, but we shouldn't use the word proof because science is tentative. So actually, eventually, the orbit of the new planet was shown to not quite be what we expected. And we're faced with the same dilemma. Should we ignore these conflicting observations? Should we modify our theory some more? Should we abandon it? What should we do? Well, in fact, there's a 4th option. Trust the theory, not dogmatically, but deducing there's something we didn't know yet. And this is beautiful. Deduce the existence of new factors. And this turned out to be true in this case. So in 1845, 2 different people, one in England, one in France, predicted that there must be a new unknown planet out there disturbing the orbit of Uranus. And they even predicted where it should be. Now, John C. Adams couldn't get anybody to listen to him. He was a young college and graduate student, and he wrote letters, and nothing happened. But Urbain Jean-Joseph Le Verrier, very famous French physicist, wrote to his friend Johann Galle in Berlin, and the first clear night after Galle received the letter, he looked and he found Neptune. It was within 1 degree of the predicted position. Amazing. In fact, the manager of the planetarium of the Institute declared this to be the noblest triumph of theory. And he has a point. If your theory lets you predict new stuff, and then you go look, I like that. That gives me some good confidence that we're on the right track. But history repeats itself. There were further failures. The orbit of Mercury was not quite what was expected. And eventually, this turned out to prove that Newton was wrong, even though the theory worked so well. And we now have replaced it by general relativity. 1916, Albert Einstein presented a new model to explain gravity. In fact, it's just space-time is warped. So the famous line, mass warps space, and then space tells matter and everything else how to move. I picture a light beam trying to go straight in warped space. Well, it's going to end up turning. And so does Earth. As it tries to go in a straight line, it ends up orbiting the sun. It works. But is it true? I hope you'll all say, not necessarily. It's not proven, right? And in fact, we already know it's wrong. because at a small scale, we have to use quantum physics, which disagrees with general relativity. And maybe, is quantum physics true? Well, again, it's an approximation. And some possible replacement theories that have been studied or are being studied may also not be the final truth. We read a theory of everything. Personally, I don't believe in this. I think we'll still be exploring new things for a long time to come. So some take-home lessons. Science is inadequate as a means of finding truth, but it's all we've got. Unless God reveals it, I'm going to do science. If God reveals it, I gratefully accept that revelation. But most of the things we have learned, we have learned because of our God-given intelligence. He made us able to figure stuff out. So I have no reason to believe that the future will be different. I think that I will still make mistakes. I think that I will still have errors in my calculations, in my observations. I think that we'll still keep learning. And there may be some experiments we never even think to try. It was brought out earlier today that creationists may try different things than the evolutionists would think of trying. And this is a big point. If you don't even think of the experiment, you can't learn. So I will take it that science gives me approximately correct answers, tentative answers. So if we try to rely on science as the only foundation of our faith, of our truth, if you will, then I think we're on the wrong track. Let's go back to the biblical worldview, which is actually a better foundation for science. Francis Schaeffer said, the Bible taught that there is a reasonable God who had created a reasonable universe, and thus man, by the use of his reason, could find out the universe's form. In fact, Christianity, biblical Christianity, gives me a reason to even believe that science should work. We understand because the universe was created by a logical God, and he made us able to study it. So with all humility, I will study the universe. I will admit that it could be beyond me, but God made me able to try. And in fact, it works pretty well, and it's fun. So awe and delight. This is how I think we should approach our study of the universe. It's like a present God gives us to unwrap. And if your child or a young relative of the family looks at the present and says, no, I don't want to do this, well, that would be sad. And I think of God wrapping this universe for us to unwrap, package. It's all packaged up, and we can try to learn things little by little. We tease out a greater understanding. We enjoy the wonders of the universe. We enjoy the process of discovery. I think it makes him happy. He is the artist. He is our father. He is the creator. And this is how I think we should face it. Kepler said, I feel carried away and possessed by an unutterable rapture. Wow, a way to study science. And he sees God as the architect. David said, the heavens are telling of the glory of God. Their expanse is declaring the work of his hands. This is how we should approach science. Ellen White says, the acquirement of knowledge through endless ages will not weary the mind or exhaust the energies. Still, there will arise new heights to surmount, new wonders to admire, new truths to comprehend. Upon all things, from the least to the greatest, the Creator's name is written, and the years of eternity, as they roll, will bring richer and still more glorious revelations of God and of Christ. We're going to be scientists throughout eternity. And for the student of God's creation, that eternity can begin now. Thank you.